All right. So in the next example, we're going to construct an antiderivative graphically. But before we do that, let's just step back and think about what we've got here. Let's suppose that capital F is the antiderivative of F, right? So what does that mean? What does that mean? That means that the derivative of capital F is F, right? Because it's the antiderivative. I take the derivative of the antiderivative, we get the original function, right? So, so essentially, this F is your derivative, right? It's the derivative of the capital F function, because F is an antiderivative. Capital F is an antiderivative of this lowercase f. Okay, so what does that mean? That means that F gives the slope. F gives gives the slope, right? The slope of 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 the capital F at any point. Any point. Okay. So, given that, let's think about if lowercase f, right, that's our derivative of the capital F, if that's positive, greater than 0 on an interval, right, then that's telling us about the derivative of the capital F. So that tells us that capital F, the antiderivative, is increasing. Okay, on that interval. Now, if it's negative, if lowercase f is negative, right, this is basically f prime. So if the lowercase f is negative, that means that capital F, the antiderivative, is decreasing on that interval. If f is 0, right? That's basically telling us that the slope is 0, right? So so f is constant. Okay, I think this, constant. Constant over that interval. All right, it gets a little confusing, except if you say capital F prime, right? That's what lowercase f is. It's capital F prime. Okay, and then it makes a little more sense, I think. All right, but capital F is the antiderivative of a function lowercase f. All right, so let's take a look at this this next example here. Now we're given a graph. Now we're told that it's a rate function. It's f prime of x, and what we want to do is construct f of x from the information that we're given for f prime of x. Okay, so let me see. Get to the right page here. Okay, so first of all, I think what I want to do is construct a table of values, right? So I'm told that, okay, we're given the graph of f prime. We want to construct f of x, and we're told that f of 0 is 10. And ultimately here we want to sketch the graph of the antiderivative, right? F of x. And so, and then we also want to give the coordinates of local minima and maxima. All right, so let's first start by constructing a table of values like we've done in the past. All right, so I'm going to construct a table of x and f of x. Okay, and I know I can use the net change theorem and find the values of f of x. Now I was given that when x equals 0, f is 0. So I'm going to go ahead and put that in there. That was given. Okay. Now, if I want another value, now notice I'm given that the area from 0 to 2 is 14. All right. So if I take the value, if I take f at 0 and add the integral from 1 to 2, or sorry, 0 to 2, 0 to 2 of this f prime of x dx, then what I'll get is f at 2. So the next point that's easy to find is f at 2, right? Now, because I don't really want to have to break this down and estimate it. I'm just going to find f at 2. All right, now f of 0 was 0. Oh, sorry, I wrote that down wrong. F of 0 is not 0. F of 0 is 10, right? That's what I was given, that it's 10. 10, right here. It says it's 10. It says it's 10. Okay, so I already messed that up. Okay, but I caught it in time because now I want, in order to find f of 2, I'm just going to take that value at 0 and add on 14, so I get 24. Okay. Now the next value that's easy to find that is 5, right? Because what I'm given is the integral, right? This area here, I'm given this area between 2 and 5, which gives me the value of the integral. Now it's below the x-axis, so I have to make sure that I count that as negative area. But I can take f of 2 and add on the integral from 2 to 5 of this f prime of x dx, and that will give me the value of the function at 5. Okay. Now, so I have to take 24 and subtract 20, right? Because this is negative area. So now I'm at 4. Okay. So, and then finally I'm given one last area here between 5 and 6. So that allows me to find f of 6. And now that's positive area. So I'm going to take the, I'm going to take f at 5 and add on that area, and I'll get 16, right? 4 plus 12 gives me the 16. All right, so that gives me a table of values, right? And now I can come down here to this little graph that I have, and I can plot those points. So at 0, we're at 10. And then at 2, we were at 24. Okay, so just a little bit below here. 24 is maybe about there. And then at 5, we are at 4. So maybe about there. And then at 6, we're at 16. So maybe about there. Okay. So that gives me some points that are on my graph. Now, before I go and just connect them up with some straight lines, I can also tell something about the concavity of the function from this graph. All right. So let's go back up a little bit and look at this. Now, so now I'm interested in the concavity, right? I'm interested in the concavity of my antiderivative. And if I'm given information about the derivative, then I know the second derivative is the slope of the derivative. So I'm going to write that out here. F double prime is the slope of f prime, right? Because essentially when I take the derivative, I'm getting slope. So the slope of the derivative is giving me information about the second derivative. So now, in order to find out whether the graph is concave up or concave down, I can look at the slope. Now it looks like f prime is decreasing, right? This is the slope here is negative, right? So f double prime is less than 0 because the slope is negative, which tells me that it's concave down, right? On this section. Maybe I'll highlight it. Maybe that would be a good thing to do, is highlight it. Let me see. I want to. So let's do down. Concave down is red. Okay, so all the way to about here. It seems to be the slope seems to be negative. Okay, now it's pretty flat over here near 0, but then if I look at the next section of the curve, you can see that it's increasing here. So if f prime is increasing, that means that so f double prime is greater than 0, which means that my original function is concave up. Okay, so I want to make sure I capture that concavity in my graph. So let's do that. Let me scroll back down. I know it has to be concave up and concave down, but let's see. There's one more piece of information we can get, right? Because right here, it seems to be switching concavity. So this is my inflection point, right? This is where f double prime is equal to 0, right? So it's switching concavity. It's switching from concave down to concave up at that point, right at about, I don't know, maybe 3.75, somewhere around in there. So I have an inflection point. All right, so I'm going to mark my inflection point. Now, I don't know the y value of the inflection point. I just know it's about 3.75, so it's got to be somewhere in here, maybe. I'll put an inflection point here. All right, and now I'm going to connect up these dots, but I'm going to have the proper concavity. So it has to be concave down and increasing, then it switches to concave down and decreasing. Okay. Now, at the inflection point, it changes concavity. It becomes concave up, and it looks like it's concave up for the remainder of the, let me draw that a little more concave up. Okay. Okay, hang on. Slippery. This pen pad is slippery. All right, I'm going to try it one more time. All right, so concave up, and then still concave up all the way to there. Okay, so all right, I'll try that one more time. Concave up. I'm trying to concave up and get it to meet up there. Okay, so I have an inflection point. Now I can also tell where my critical points are. This is a critical point. This is a critical point, right? The critical points are where the derivative is 0. So this is a critical point, and this is a critical point. You can see that those are my local, this is my local maximum, and this is the local minimum down here, local minimum down here. So I have a local maximum at 2,24, right? And I have a local minimum at, what was that, 5,4. Okay. Now those are also my global maximum and minimum over this interval, right? When I find global maximum and minimum, I have to include the endpoints, but you can see these endpoints are not as they're not as high or low as the local minima and maxima. So these are also global. Global. Or I think your book uses, I should probably use it. I think your book uses absolute max and min. Okay, those are also the absolute max and min. Okay, so just to kind of, we took into account the slope of the function, right? Because you can see that the derivative is positive and then it's negative, so it goes from increasing to decreasing at 2, and then and then it's positive again after 5, from 5 to 6, and so it's increasing there. But we also took into account the concavity. So let's summarize what we learned. So if, again, this capital F is an antiderivative of f, right? That means that the second derivative is second derivative of the capital F is the derivative of f. Okay, so we can determine the concavity of the graph of capital F based on the properties of the derivative. And so if the antiderivative, right, if the, sorry, not the derivative. All right, so capital F is the antiderivative of f, right? So that just means that capital F prime, oops, capital F prime is equal to f, right? So because capital F is the antiderivative of f. I don't like the fact that these have the same letters, just one's a capital. Right, so that's what the antiderivative means. But that means that f double prime is equal to f prime, right? All right, so f prime, if it's greater than 0 on an interval, that means f is increasing, and the graph of f is concave up on that interval, okay? Because the derivative of the derivative is the second derivative, okay? Now, if it's negative, then f is decreasing, and capital F is concave down on that interval, okay? And we have an inflection point in the antiderivative, f, capital F, where f changes from increasing to decreasing, or vice versa, right? So basically at the maxima or the minimum of f, lowercase f. All right, I feel like that seems more complicated than it is. I think it's partly just because we're using capital F and lowercase f. Oh my God. Okay, so hopefully the example makes more sense, right? To you that we're looking at the slope of the derivative to find the second derivative. Okay. All right. I will meet you in the next video for the final example.